12:01, so I'm going to pass it on to the student moderators and we'll get started.
All right, thanks, Dan. All right, so I'll be moderating today. My name's Aaron, and we'll go through Mark's Royer's first talk, and then we'll go through, I believe, Ann, you're reviewing Joe's talk about the similarities, and then we'll move on to the presentations. All right, so last week we first heard from Mark Royer. He's a computer scientist working with CHA. The title of his presentation was A Design for Loosely Coupled Scientific Applications. Okay, and so the problem that they were facing is that there's technological advances in earth sciences and climate sciences, and the amount of data that has come out of these, out of the amount of research that's been happening has increased, and along with access to that data. But analyzing those large data sets is complicated and usually requires a steep learning curve. And within each separate lab that is analyzing that data, the methods can be slightly different. So the goal was to create a user-friendly software that is widely available on different platforms for scientific data analysis, which can be run on a local, so your desktop or mobile device, or remote, so a server environment. So to do this, they proposed a software architecture that through a virtual machine uses representative state transfer, or REST API, and transpiled shared code to create, store, and manipulate data. There were 4 components of this application. There was the Java classes, the REST API server, the Java script, which is transpiled from the Java classes, and the application front end, which uses both data from the REST API servers and the Java script. So as a seed project from this, Mark created the git.icecordedata.org website, which allows for users to use and understand different iSquared data. That allows for statistical and visual analyses.
All right, and now I will discuss the other talk we heard last week, which was from Joe Mohan, and it was on defining the Anthropocene and the consideration of the sediment archive from Herd Lake, Idaho. And we learned that the decision on whether to officially declare the present time in geologic history as the Anthropocene lies with the Anthropocene Working Group, which is a subgroup of the International Commission on Stratigraphy. And in 2019, the group actually did vote to designate the Anthropocene as a new epoch. And this decision brought into question how we will define the start of the Anthropocene. So what event will mark this boundary between the Holocene and the Anthropocene? And the event would need to be visible in the stratigraphic record throughout Earth. And often these boundaries are marked by biological events. So where fossils are visible in one layer, but then they are absent from the succeeding layer. And suggestions for the beginning of the Anthropocene included the first appearance of agriculture, the eruption of Mount Tambora, the colonization of North America, the invention of the steam engine, and the first nuclear bomb testing in 1945. And this last suggestion is the most popular, as it is the most apparent globally in the stratigraphic record. And scientists use something called the golden spike, which is this metal plate that's placed somewhere in the world along the stratigraphic boundary between the two epochs. And it serves as an example of that specific transition. And for the Anthropocene, the golden spike location, and for all of the golden spike locations, they must have fixed sediment, and it has to be continuous sedimentation and fast deposition and be undisturbed, as well as have well-preserved fossils and a long-range correlation. So something that can be seen across the world. And Joe Mohan suggested Herd Lake, Idaho as a potential location for the golden spike to delineate the Holocene-Anthropocene boundary. And this is because sediment cores from the lake have clear varves, which are alternating light and dark sediment bands, with each pair representing a year. And they date back 1,300 years. And the varves include a visible signature of the atomic bomb testing. And this signal is found in varves worldwide.
So I'm going to kind of talk about both papers taken together. And what really struck me was the way these two papers, in very different ways, tackle the issue of how we store, mark, and access data and knowledge through time and space. Both papers ask, how do we embed, either digitally or physically, particular logics or markers that enable compatibility and continuity of knowledge across a variety of contexts? For Mark, the problem is in part the rapid fire evolution of platforms and operating systems and their overwhelming diversity, and also changing social patterns in terms of where we perform our work, whether from a computer lab, the field, or the comfort of our own living room, which we might have become kind of accustomed to during this pandemic. So how can we engineer the applications that we rely on so that they're broadly compatible with various devices, and so that they don't become living fossils of bygone technologies? On the other hand, Joe investigated the system that's used to construct the geologic timescale, which we can consider a common language across the earth sciences for relating events and establishing a shared global history. But when it comes to defining the Anthropocene, Joe's presentation and the ensuing discussion reminds us that generating consensus is no small task. Defining the Anthropocene is made more challenging because there's diverse stakeholders, not just the geosciences, but the social sciences as well. And each of these have their own applications, their own perceptions, their own front-end languages, we could say. Mark and Chaw's solution to satisfying diverse front-end applications is an architecture that emphasizes flexibility and relationality. Data and functions are centralized in a remote environment or virtual machine, but they're made available through a transpiler or translator and a programming interface that manages client requests. While it might seem counterintuitive, by making space for diversity, this approach actually promotes continuity and shared understanding between users. Joe asks us to think outside the rocks and consider demarcating the beginning of the Anthropocene with virtual golden spikes in the sediments of barred lakes, like those at Herd Lake. Annually resolved sequences provide the opportunity for precision far beyond what we find at other geologic boundaries. However, as Paul pointed out in the discussion following Joe's presentation, some of the patterns that mark the beginnings of geologic periods, including the Anthropocene, occur over many hundreds to thousands of years. And so there are many who will continue to struggle with the AWG's definition of the mid-20th century boundary for the Anthropocene. But setting aside the decisions and authority of the AWG for a moment, perhaps Mark's approach in managing diverse front-end applications holds a lesson for approaching the definition of the Anthropocene and aiming for flexibility and relationality. Rather than honing in on a precise moment in time or a specific geologic context, we might be well served by instead defining a set of characteristics or features that can be applied as needed to a range of geo and social science contexts and environments, from lake or marine sediments to ice cores to archaeological sites, or even the pages of historical documents. So I encourage Joe to continue advocating for his non-traditional context for a golden spike.
All right. So up first, we have Frankie Amand with talking about mollusk bivalves as El Nino Southern Oscillation, or ENSO proxies.
Thank you. I don't think I'll be nearly as poetic as Elizabeth, but I'm going to share my screen and get started. Okay, can you all see this? Great. So, hi, my name's Frankie Amand, for those of you who don't know me, and I'm going to be talking about my dissertation research that I've been working on while in the interdisciplinary PhD program, and I'm also a student of the CCI. So I'm going to be discussing high resolution sea surface temperature satellite data, as well as my newfound skill in computer animation of oceanic monitoring buoys and mollusk bivalves. I'm just gonna try to minimize this. There we go. Okay, so broadly speaking, my research is an effort to assess the strength and nature of the El Nino Southern Oscillation signal in the oxygen isotope ratios of modern Peruvian bivalves or shellfish. And I'm hoping that the results of this work are going to inform and help us refine sea surface temperature reconstructions of past environments and ENSO conditions using archaeological materials. ENSO is characterized by aperiodic shifts in both atmospheric pressure and sea surface temperature, or SST, in the east central equatorial Pacific Ocean. Primary impacts, mostly seen on the north coast of eastern Pacific and coastal El Nino warming events, two components of ENSO, manifest as sea surface temperature anomalies, and on land as heavy rainfall, flooding, as well as erosion. These events have affected the entire Peruvian coast for over the past 12,000 years. And so my goal here is to try to help improve our understanding of bivalves, which we use as proxies commonly in ENSO research, to help better articulate the differences and the similarities between regional ENSO records here on the north, central, and south coasts of Peru. So my dissertation covers a number of topics. I'll talk briefly about each of my three primary objectives and kind of just give some background on where I'm at with my research. My first objective is to assess variation in the oxygen isotope ratios of oxygen 16 or 18, a value known as delta O18. So to assess the variation of the delta O18 signatures of different bivalve species found along the coast of Peru, so I can try to relatively rank their reliability as ENSO indicators. I will be doing, to accomplish this, a cross-species comparison to assess the strengths and the nature of the sea surface temperature signals. And I'll be comparing these isotopic-derived sea surface temperatures that I get from my samples, as well as from samples from colleagues. I'll be comparing these to instrumental records. So in 2019, I harvested bivalves growing in harbors in Peru, harbors that had IMARPE sea surface temperature monitoring buoys. I went to Lima and worked to prepare these samples for analysis at the University of Cayetano Heredia. And what I did was worked to identify bi-monthly and monthly growth increments in these samples so that I could drill them and then perform isotopic analysis, which I'm excited to say I'll be able to do this week as I send my samples finally to Iowa State University to Al Wanamaker, a CCI alumnus and also a member of my committee. So I'll be getting the results of the delta O18 signatures from various samples that I collected. And then I'll be comparing these to sea surface temperatures from the same time period that they were alive. Some of these a year and a half, some up to 4, maybe more than 4 years. So I can try to assess which species more accurately reflect these instrumental records. My second objective is to evaluate some bivalves that haven't been well studied in terms of their utility as ENSO proxies. This involves determining if we can even find growth increments in these shells and if we can use their isotopic signatures to understand marine conditions. And so this involves similar methods in which I prepared these shellfish for microscopic analysis and growth increment identification in order to try to drill them to do isotopic analyses. I'll just touch on one of these bivalves is Tavilla hyans. I wanted to know when I started, are their growth increments even identifiable? And I was excited to find that yes, they are. I could identify not only monthly, but bi-monthly and even more frequent growth increments in these shells. And so my next step after drilling from the bi-monthly growth increments is to send the samples off to Iowa State University to understand if either their biomineralization patterns or their oxygen isotope signatures do in fact reflect sea surface temperature conditions. Will these be reliable proxies for sea surface temperature or for ENSO events? This is important for a number of different reasons. On the North Coast, there are a number of beech ridge plains that are time transgressive. They formed over many thousands of years. And here are the Chira Beech Ridge Plains. It's a 31-kilometer long set of 9 beech ridges. And like I said, these span several thousand years, dating from the mid-Holocene. And each ridge is capped with bivalves, including many Tavilla hyans, which I've been focusing on, that were harvested and discarded by humans over a several thousand-year period. In fact, interestingly, these shellfish valves have protected these geomorphological features from erosion over time. And that has been shown by research by Dan, Kirk, and others here at Maine. So the potential here is that if Tavilla hyans oxygen isotope signatures do record ENSO events or sea surface temperature change, this would be really useful because I'd be able to select a number of samples from each of the ridges, which are all well constrained temporally using radiocarbon dating already. And I'd be able to help reconstruct marine conditions in this area. And moving on to my third objective, which is to assess the agreement between more local sea surface temperature records. I've talked briefly about the bivalve Delta 18 and the buoys, and comparing these to more regional sea surface temperature records, such as satellite data. So in this component of my project, I'm comparing modern bivalve reconstructions to instrumental records from the buoys and also from satellite platforms, with the goal really of assessing the accuracy of the coastal satellite sea surface temperature data. The sea surface temperature satellite data is, I'm calling regional. It's a 1 kilometer pixel, which is good for sea surface temperature oceanic data. However, 1 kilometer span doesn't really reflect the local growing conditions of a single bivalve. So for that reason, I wouldn't refer to it as local. But what I want to do is take the bivalve signatures, here's just a subset of data, an example, and take their Delta 018 signatures, calculate from that sea surface temperature, and then compare those to the buoys from which they're harvested nearby, as well as the satellite data to really get a closer understanding of what are the differences and what are the strengths of the bivalve data, as well as the satellite data. Is it accurately reflecting along the coast the in situ records from Imarpe? And lastly, I just wanted to share this targeted ad I got on Amazon last week. This is a beach towel of Anandara tuberculosa, another one of the bivalves that I'm studying for my second objective. So thank you all. Looks like I finished a couple of minutes early. And if anyone has any questions, I'd be happy to answer them.
All right, thank you. Does anybody have any questions?
Hey, Frankie, I have a question for you.
Go ahead, Elizabeth.
Particularly deep one. I was wondering why you chose to focus on the Chira Beech Ridges versus other beech ridge complexes in Peru.
Yeah, well, I feel like the Chira Beech Ridges there's a lot of potential there for further research, and the 2 species that are predominantly found on the ridges haven't had a lot of attention to Velahyans. The other is Donax abeslus, which Jacob Warner recently received a Society for American Archaeology award for his research on. But I would say that these two bivalves, I think there's a lot of potential. They're both North Coast bivalves. And so I was interested in focusing here because I saw an area for improvement or for future study. There, like you mentioned, are definitely other North Coast Beech Ridge sets. And I think there are some similarities, their timelines of formation and the potential relationship there with ENSO. But I feel like there has been some additional research that has maybe been performed on those. So, yeah.
Okay, I have a quick question for you. What are the depth ranges in the different bivalve species, and how wide is that range?
Yeah, that's a great question. And so it varies. And I think that probably what you're getting at is, do their locations of growth and the sea surface temperature monitoring buoys, like what's the discrepancy there?
Right.
Yeah, so for instance, I harvested some Argopecten purpuratus. I didn't harvest them, but I went on a boat with some fishermen who I had hired to dive for them. And these particular ones were probably growing 5 to 10 meters underneath the surface. And so what you're going to have to be doing with the bivalve isotopes is there's a lot of variables, including the difference between the depth of the sea surface temperature buoy and where they grow. Also things like freshwater input into the area or upwelling. And so luckily there's not a lot of freshwater input, but as far as that distance goes, that's something I have to take into consideration when I'm looking at the isotopic values. And so whereas maybe they're might not be, they're not going to give me an exact representation. Oh, that's my timer I set for myself. I'm hoping to see a linear relationship nonetheless. Okay. Yes, but you've touched on one of the difficulties of this research, and some of them, like clams, are intertidal, and so there are definitely differences in their exposure to different marine conditions. And some of these even shut their valves. Say when clams are exposed, they shut their valves and they stop biomineralizing and growing. And so, yeah, there's definitely complications. And I think that it's possible to overcome some of those and still get some interesting results.
Okay, neat. Thank you.
Thanks for your questions.
All right, is there any other questions? All right, well, if not, thank you. And we'll move on to our next speaker, Hunter Tubbs, who will be, his title is Coupled Model Sea Surface Temperature Biases and Their Influence on Tropical Cyclone Environmental Conditions in Atmospheric General Circulation Model.
You're still muted, Hunter.
Can you hear me now? Sorry.
Yep, you're good.
Yes.
All right, just trying to share my screen. Can you see my screen now?
Not yet.
All right, sorry. How about
There it goes.
Sweet. Just gonna move this out of the way. Oh. All right, everybody can see it? Sweet. All right, so good morning, good afternoon, everybody. I'm gonna switch focus a little bit today with my presentation, which, as you said, the title is The Influence of Coupled Model Sea Surface Temperature Biases on Tropical Cyclone Environmental Conditions. And to start off, I'd just like to thank my thesis committee, Sean Burkle, Benjamin Lintner, Kirk Misek, and my thesis advisor, Bradfield Lyon, as well as NSF for supporting this research. So to start off, we're going to talk about the oceans. So as we know, the oceans play a fundamental role in the global climate system, with over 70% of the global surface covered by them. So the ocean surface is extremely important, as it serves as the interface between the ocean and atmosphere and can actually result in changes in atmospheric circulation patterns, which is what we see in ENSO phases. So for example, I have plotted here the extended reconstructed sea surface temperature observed climatological values. And we can see that generally speaking, there are warmer sea surface temperatures throughout the tropics. However, it's not completely uniform. So for example, off the west coast of South America, we can see an area of comparatively lower sea surface temperatures, which is associated with the eastern equatorial Pacific cold tongue. And then we can see warmer sea surface temperatures across the western Pacific with the Pacific warm pool. Also plotted here, which is a little bit tough to read, I apologize for that, are contour lines. And these contour lines show average annual precipitation in millimeters per year. And from this, you can see, if you look really closely, that the higher precipitation rates are often associated with warmer sea surface temperatures, with comparatively drier conditions across areas of cooler sea surface temperatures. And this is due to processes such as evaporation and atmospheric instability, which we won't go through too much here. So, like I said, sea surface temperatures can alter regional climate conditions, not only just in the tropics, but also outside of the tropics. So for example, on the left-hand side, I have the October to December 2015 SST anomalies, which happened to be a strong El Nino year, or ENSO warm phase. And we can see across the Eastern Pacific, there were sea surface temperature anomalies between 3 to 3.5 degrees centigrade above average. When something like this occurs, we can see changes in the average climate across, like I said, the globe. So on the right-hand side, we can see average conditions during a moderate to strong El Nino condition or year. So for example, in New England, we typically see warmer than average conditions, as well as across portions of Alaska, whereas the southwestern United States tends to be wetter, the southeastern United States tends to be cooler, and then we also see global changes as well. During La Nina or ENSO cold phase, these conditions are about opposite. It's also important to note that these can alter tropical cyclone environmental conditions. So for example, during this El Nino year, there was a huge increase in tropical cyclone activity across the eastern tropical Pacific Ocean that year, which broke a lot of records actually. So my project is to examine the influence of these coupled model sea surface temperature biases on the atmosphere. So to do that, I use two atmospheric general circulation models. Specifically, I'm going to be looking at the environmental conditions for tropical cyclones. So as we know, climate models have evolved substantially from when they started. They now have better resolution through the horizontal axis as well as the vertical axis. They're able to include complex processes such as the hydrological cycle, the interaction with the Earth's radiation budget, and among other things. However, despite all of these improvements, there are still well-documented issues with some of these models. So for example, the top right-hand panel shows the multi-model, which is a 31 model difference in sea surface temperature between climatology and the CMIT 5 historical runs in degrees centigrade. And we can see that in this plot that there were sea surface temperature anomalies or differences between the control runs and observations between these SST biases, where there were differences of between 1 to 3 degrees centigrade in generally the same area as the El Nino plot that I had shown earlier. And there's even localized areas right along the coastlines of where upwelling tends to occur of 4 degrees centigrade. Regions of upwelling are known to be particularly troublesome for models of this sort. So it led to the question, well, if it's producing these El Nino type conditions, is it possible that in their own simulations, they're creating their own El Nino ENSO type climate conditions? So you may also ask, why am I studying tropical cyclones all the way up in Maine? So it is true that most tropical cyclones do form in the tropics, as you can see in the bottom right picture, which is historical tracks and intensity of all tropical cyclones. We can see, just as expected, most of them do form in the tropics, especially the stronger ones. Also note that there's very few, if any, right along the equator where the Coriolis force is equal to 0. However, you can also see if you follow some of these track lines that they do happen to often get into the higher latitudes, including here in New England. And there was even a couple of cases this past year where the remnants of tropical cyclones made it all the way up into New England. And despite them not being, strong category 2, 3, 4, or 5 hurricanes, they still can pack a punch. So considering the large impacts that these storms can have, including storm surge, heavy rainfall, and strong winds, it's still a worthwhile project, especially considering this has not been looked at too deeply in the literature. So my approach. So I'm going to analyze, or I already have in most cases, analyze the output from idealized climate model experiments. So I have 2 runs, the control runs and the bias runs. So like I said, I use atmospheric general circulation models, and I'm using an ensemble plume. An ensemble is essentially rerunning a model multiple times with slightly different conditions to see how the model behaves. So I have 16 ensemble members, and then I have control runs for those 16 ensemble members and bias runs. The control runs, I run the model with observed sea surface temperatures between the period of 1979 and 2004. These runs were already completed prior to the start of this project, I should note. I'm simply just using the output. And then there were also bias runs where the model was ran with observed sea surface temperature plus the SST bias for a similar time period. Through that output, I then use MATLAB and other programming languages to compute tropical cyclone indices, which relate atmospheric and sea surface temperature conditions. So the first of these indices is something called the Tropical Cyclone Genesis Index, which is essentially the frequency or the likelihood of a tropical cyclone to form in a particular area for a given time. And this was developed by Tippett et al. 2011. There's also another index called the Tropical Cyclone Potential Intensity, which essentially says if a tropical cyclone were to form in these conditions, how strong could it theoretically become? And that was completed by Manual 88 and Blitzer and Emanuel 2002. So first, we're going to compare the results for the above indices computed from the control run data with observations or reanalysis. And then we're going to examine the differences in the indices when computed using bias and the control runs and see how these biases are in fact influencing, if they are, these calculations. So for example, here I have some results. So this is the TCGI, so Tropical Cyclone Genesis Index for the control runs versus the observations using, using reanalysis data. So I used extended reconstructed sea surface temperature version 4 for SST and NCEP reanalysis for that. So I'm sorry, I skipped one slide. So TCGI. So I know that we're not supposed to show equations in PowerPoint. I'm going to break that rule just temporarily because it is important to see the math a little bit. So this is actually one of the easier of the 2 equations. So I'm going to show this one instead of the potential intensity equation. So TCGI is a statistical fit between the climatological number of tropical cyclones in a given month and different environmental, large-scale environmental factors. So for example, this is a exponential equation where the left-hand side term mu is the expected number of tropical cyclone genesis events per month in a 40-year record. The next term is the 850 hectopascal absolute vorticity. Vorticity is just a fancy word for spin, essentially, in the atmosphere. And absolute vorticity is simply the sum of the relative vorticity and the planetary vorticity. We then have the 600 hectopascal relative humidity. Relative humidity is the amount of water vapor in the air at a given temperature. We need moisture or relative humidity in order for a cloud to form and for precipitation to form, which is important for tropical cyclones. We then have T, which is the relative sea surface temperature, which is the difference between the local sea surface temperature and the tropical average from 25 south to 25 north. And this is useful because it allows for changes in the mean climate. We then have V, which is the 850 to 200 hectopascal vorticity, and vertical wind shear. And vertical wind shear is simply the change in wind direction or speed with height. and it can also be both. Tropical cyclones are known to be sensitive to all these terms, and that's why they are shown in the equation here. The last term, cosine phi, phi is just latitude with the dependence on where the storm's actually originating. So now we can see the results. So on the left-hand panel, we have reanalysis data. So TCGI calculated using ERSST version 4 and NCEP reanalysis. And we can see through this plot, there's a couple of areas of enhanced tropical cyclone activity, including in the Western Pacific, the Eastern Pacific, as well as portions of the Gulf of Mexico, with on average about the maximum about 16 to 20 storms or so. On the control run, which is shown on the right-hand side, we can see fairly similar results. However, there are some differences. In terms of the areas of enhanced tropical cyclone activity, they are lying in the same areas, generally speaking, which is a great thing to see. However, they are generally overestimating the number of tropical cyclones compared to the reanalysis data on the left-hand side. So just to give a little bit better idea here. So as I said, they tend to do a pretty good job of capturing the overall observed pattern. And in order to show that more mathematically, I calculated a pattern correlation coefficient with a value of 0.98 obtained. And as we know, we want the value as close to +1 as possible. So the model is doing a very good job of capturing the overall pattern. However, it does tend to be overestimating a bit, at least in the control runs compared to reanalysis data, the number of the tropical cyclones. We then look at the bias runs. So this is a difference plot between TCGI calculated from the atmospheric model, ECM5, bias runs minus the control runs. And again, we can see a very high pattern correlation coefficient of 0.99. However, it does tend to be either overestimating or still underestimating areas of tropical cyclone activity, with areas of underestimation occurring in the Eastern Tropical Pacific, overestimation occurring in the Western Pacific, Northern Indian Ocean, as well as portions of the Gulf of Mexico. It is important to note, though, this is just one reanalysis product, ERSST version 4 and NCEP. So we're kind of assuming that this reanalysis is correct, and it is possible that it's prone to its own biases and inaccuracies. So another step in this project would be to look at another reanalysis product just to see the differences between just reanalysis products themselves. So future work. So I'm going to complete comparisons of TCGI and PI, potential intensity, for bias and control runs, including an evaluation of statistical significance. Those were statistically significant differences, but we will be looking more closely at also which environmental terms, so out of those terms that went into the equation, which are contributing most to those overall changes. We're also going to identify statistically significant differences in potential intensity between the bias and control runs, and again, compare that to NCEP reanalysis. I'm also going to finish completing writing my thesis and continue to get as far along as possible. That's all I have, so I'll take any questions that people may have.
All right, thank you, Hunter. Does anybody have any questions?
I have a question, I guess. Can you say more about these fake El Niños that you think the models are creating, if I understood you properly?
Yes, so it's not so much that the issue is that the bias runs, when you compare that, so let me just go back a couple slides. So for example, on the top right panel, that would be the multi-model mean SST bias. And if you compare that plot to the El Nino year of 2015, you can see that the areas of warmer than average sea surface temperature, the positive SST anomalies, they're essentially in the same general area, and the order of magnitude is also pretty similar. So it's not so much that they're producing a fake El Nino per se, but the SST biases themselves are kind of representing, or they kind of look similar to an actual El Nino event. So part of this project is to determine whether or not these biases are actually creating their own El Nino type patterns in their climate simulations.
Thank you.
Yep.
Right. Does anybody else have a question for Hunter? All right, if not, we'll move on to our last speaker for today. So Madelyn Woods will be giving her presentation, and it's titled "A Key to Past Ocean Temperatures: Magnesium-Calcium Ratios of Foraminifera Calcite in the North Atlantic."
Hi, there we go. Now I can share my screen. Oh, I did that. Let's try this again. One more try. Sorry, everyone. Never done this before. All right.
There you go.
Can you guys see just my PowerPoint now?
Yep.
All right. Sorry, for some reason it switched the presenter view, so I won't be able to look at you, but at least you can see my screen. So hi, thanks everybody for coming. I'm going to be discussing my PhD thesis with you, in which I hope to use the magnesium to calcium proxy in foraminifera shells to create a more robust reconstruction of ocean temperatures over the Holocene, specifically in the Northwest Atlantic. We are living in a warm interglacial climate. The Holocene spans roughly the last 11,000 years and is generally characterized by long-term shifts in mean conditions, such as sea surface temperature and ocean circulation, that have been punctuated by abrupt ocean climate events. But the causes of these events and shifts are not fully understood. So paleo reconstructions provide essential context for understanding and predicting modern climate change. This graph shows the Alkanome proxy data that is presumed to represent mean annual sea surface temperature in the Northwest Atlantic. You can see that there is a significant cooling illustrated here over time, but this is a much larger cooling that has been seen in other places of the Atlantic. In the Northern Hemisphere, annual solar insolation was fairly stable during the Holocene. So if the alkanones here are reflecting the mean annual sea surface temperature, why are we seeing such a large decrease? So one explanation could be that the proxy is seasonally biased, but there's also the possibility that climate variability isn't driven by solar installation, but caused by internal feedbacks in the ocean climate system. In the Northwest Atlantic region, we have warm, salty water from the south, which mixes with the fresher, colder water from the north, which results in a net northward transport of heat and a net southward transport of fresh water. The Gulf of Maine is filled by both of these northern and southern sourced water masses, and changes in the nature of transport in either one have been linked to changes in overturning circulation and buoyancy fluxes, which make this region susceptible to climate feedbacks. Because the Northwest Atlantic and the Gulf of Maine in particular sits at the confluence of major atmospheric and oceanic currents, it's an ideal place to monitor Holocene ocean climate dynamics because it's very sensitive to greater regional changes in ocean and atmospheric circulation. With my research, I want to understand how conditions here have changed in the past. And so one way to do that is to reconstruct the oxygen isotope and temperature composition of seawater, which can help understand the relative influences of incoming water masses and provide insight into past climate change. So establishing high resolution records for this region will provide insight into long-term Holocene cooling, abrupt ocean climate shifts, and amplitude in variability during different mean states, so a warmer or colder than present world. So I have 3 research goals. First and foremost, I want to generate continuous ocean temperature records in the Gulf of Maine region for the past 11,000 years. I also want to estimate the seawater oxygen isotope ratios to gain insight into the ocean circulation in the Western North Atlantic. And I also want to field test existing magnesium to calcium proxy calibrations in the North Atlantic, and if I can, quantify secondary controls on the relationship using the species Neogloba quadrina in Compta. So a really useful way of monitoring changes in ocean circulation is by monitoring the oxygen isotope composition of seawater through time. So the transfer of oxygen isotopes between different reservoirs is dependent on both the mass and temperature, and different processes favor one isotope over the other. Lighter isotopes are more readily evaporated than heavier isotopes, which is called fractionation, and the transfer of lighter O16 over the heavier O18 from seawater to air changes the isotopic ratio of both the atmosphere and the ocean, so making the air values more negative and the ocean values more positive. Precipitation further depletes the O18 in the atmosphere, and by the time the air is circulated to the poles, the deposited snow is very rich in O16. So during colder periods with larger ice sheets, we have more O16 locked away in the ice and more O18 present in seawater, which means there's more O18 incorporated into the carbonate shells of marine organisms. The opposite is true for warmer periods where we have ice melt, which releases O16 enriched meltwater back into the ocean, producing more negative values of seawater. And there are other factors that play roles in the isotopic composition of seawater, but in the Gulf of Maine, we're mostly concerned with temperature and ice as major drivers. So on the left, you can see a map of the delta O18 measurements from the upper 5 meters of the water column. And you can see just how much it varies spatially in the North Atlantic. And on the right, you can see the major water masses that I was talking about earlier, characterized by different O18 signals. So here we have the Gulf of Maine in black, excuse me, the Georgia Slope water in red, the Labrador Shelf in blue, and the Scotian Shelf in green. Excuse me. So by creating high resolution reconstructions of circulation via temperature and the O18 composition over the Holocene, we can gain a better understanding of how the system was changing. So one of the principal proxies used for determining paleo sea surface temperatures is the ratio of magnesium to calcium in foraminifera shells. So foraminifera, or forams, are single-celled protists that form a calcium carbonate shell. They live at all depths of the water column and are one of the most abundant fossil records in the marine environment. Those pictured here are some of the more common species that I've been finding downcore in the Jordan Basin. The top row are planktonic species and the bottom row are benthic species. Neogloba quadrina incomta, or N. incomta, is the dominant planktonic species in the Gulf of Maine and a major component in North Atlantic water from spring to fall. So it will be the main species used in my temperature reconstructions. The underlying basis of the magnesium to calcium paleothermometer is that the amount of magnesium in calcite that has been precipitated from seawater is dependent on the surrounding temperature during calcification. So specifically through an endothermic substitution of magnesium for calcium, where the partitioning of the magnesium solid increases exponentially with temperature. This figure is from a study by Morley et al., where they calibrated the relationship of the magnesium to calcium ratio with temperature. While you could fit a line through this data, you can see there's quite a bit of scatter still. And so what they did was to develop and apply a calibration for the carbonate ion concentration in seawater. So recent culturing experiments of forams have revealed a significant relationship between magnesium composition in forams and the carbonate ion concentration of seawater, where the ratio of the magnesium to calcium increases with decreasing carbonate ion concentration. So this means that the magnesium to calcium ratio in forams may be biased to higher values in paleoceans that had significantly lower carbonate ions than modern seawater. But because this calibration and the correction already exists in the North Atlantic, one of our first steps will be assessing whether it can be applied to our Gulf of Maine samples. So corroboration of these calibrations would increase the the confidence in the use of the magnesium calcium proxy across different regions. But if the numbers don't match, we still have a way to produce our own calibration specific for the Gulf of Maine using samples that we hope to collect next summer. So next August, we will hopefully be conducting a research cruise in the Gulf of Maine. The majority of our sites will employ both multi-core sediment samples and hydrological samples, indicated here in yellow. So hydrological samples will consist of contemporaneous plankton tows and hydrological profiles of basic seawater properties, such as temperature and salinity, and we'll also be collecting whole water seawater samples at depth for analyzing the O18 and the carbonate chemistry of the seawater. On top of that, we'll also be collecting more core top and down core samples at strategic locations along the cruise site. So this is a really multi-angled approach to this questions. Back in the lab, our forams will be analyzed in two ways. So the majorities of sample will undergo traditional bulk ICP-MS analysis. These bulk samples will the bulk samples of whole shells will be crushed and dissolved and run through the mass spec to measure pooled elemental composition. And this is to help facilitate meaningful comparisons with previously published studies. However, as a supplementary aspect to understand the variability of magnesium within our foram populations, we'll also be applying laser ablation techniques at each stage of the process. So selected individuals will be mounted and a profile drilled through their shells for single shell measurements of the elemental compositions, such as those seen here. So just to sum up, the questions that I'm hoping to answer with my reconstructions is: one, did the Gulf of Maine ocean temperatures follow a smooth regional trend through the Holocene, or did they exhibit abrupt shifts? And was ocean temperature in the Gulf of Maine region more variable during the warmer than present Holocene or less variable? And before I end, I would just really like to thank the many collaborators we have on this project, because it is very large and has lots of components, and it would not be possible without a lot of help. And with that, I will take questions. Thank you.
All right, thank you. Does anybody have any questions?
Hey, Madelyn, I have a question. You talked about the different types of cores you were taking. What is a paleo core?
Oh, sorry, did I say paleo core? I definitely meant down core. So when you're taking cores, you can take like a surface core, which is the first couple, the first top of the sediment that's sort of been churned up. It's considered a core top. And then the down core samples are really the layers that we hope to look at paleo records with. So older than 100 years, I think, in our region mostly.
Cool, thank you.
Yeah.
What's the time resolution of the cores in the Gulf of Maine?
The past in the Jordan Basin, I think we're hoping to get 200 years resolution because the sedimentation is quite high in some of the deeper basins, which is where we've sort of strategically placed our cruise track.
And has that been constant throughout the Holocene?
Throughout the Holocene, I don't know, because most of the records don't go back as far as we are going.
Okay.
So we will find out.
If there are no more questions, a quick announcement and then a quick summary. I want to remind everybody that next week we do not have a regular Borns, but instead a guest speaker, Dr. Robert Ackert from Harvard, talking about constraining interglacial ice sheet elevations in the interior of West Antarctica at this same time, and I believe at the same place, but I know Becky sent out the link for everybody. In terms of the talks today, I'll start with Frankie. And given that I'm one of Frankie's advisors, it's perhaps shellfish to say how much a talk on El Nino and mollusks warms the cockles of my heart, but I'll say it anyway. Past attempts to build species-specific isotopic calibrations for sea surface temperatures with mollusks in Peru have had variable success. One might say they have run hot and cold. Frankie's approach to collecting samples and environmental data at point of collection has real growth potential for advancing this proxy's utility in understanding the paleo record of ENSO, even if success proves to be incremental. Her proposed study of Tivoli on the Chira ridges could ruffle current thought on Paleo El Niños, and if you're as old as I am, then you know that ruffles have ridges, so why not vice versa? Hunter Tubbs has chosen to address a very stormy topic on problems in modeling tropical cyclones. I was taken with the possibility that the models may be creating their own El Niños. As you know, El Niño is named for the Christ child because it often appears in northern Peru at Christmas. So model-made El Niño is a perfect case of a deus ex machina. And Hunter found that the models overestimated the number of tropical cyclones, so it sounds like the models are spinning the results and overselling them. Finally, Madelyn addressed another cool topic, Holocene sea surface temperatures in the North Atlantic, which she approaches by estimating Gulf of Maine temperatures over time through isotopic ratios and forams. As a common approach, forams aren't a hard sell as a proxy, but the devil's always in the details. And in this case, Madelyn's core work will be to try to see if the North Atlantic calibrations work for Gulf of Maine samples. Thank you all, and see you next week at the talk.
See y'all. Thanks all.